I'm very happy to welcome you here for this conference celebrating Andrew Granville's 60th birthday. I met Andrew about 20 years ago when I moved to Montreal from France, and he had just moved to Montreal from Georgia. And one of the first things I did, I started to chat with him, and then I went to inspect his office. And I discovered that his office was twice as big as my office. So I was very shocked with that. But then I realized that his blackboard was half of mine. So I thought, okay, that's a draw. It's okay. And then we started to talk about many things, we touched on many subjects, and I was always impressed with his energy and enthusiasm and stories too. And one of the subjects we touched about often was how our new institution is working in administrative matters. We still touch on that a little bit these days. And in all this topic, I always had the last word, because I always could say that in France, things are even more difficult and it's even more complicated. And also we talked about other things about math quite often. And he tried to educate me in number theory a little bit, because I'm a topologist and geometer. And I tried to tell him things about geometry and topology. And I enjoyed these discussions very much. And one thing that happened is that in each about 2 months or 3 months, he would tell me that there's a new breakthrough in number theory. And he would also say that some of his students or former students or postdocs have been involved. And after a while, I started to think, okay, this guy is very, very nice, and I enjoy talking to him, but I wonder a little bit about his standards. How could there be breakthroughs all the time and his postdocs, students be involved all the time? But then some of the numbers I remember from that time were Radziwill and Matomaki, and later on Maynard. So I think about that, he had the last word. So I'm looking forward to many more about breakthroughs in number theory in years to come, and want to wish Andrew a happy birthday, and welcome you all here, and hope that this conference will be very, very good and you'll enjoy it. And I'll pass the mic to Dimitris.
Thank you, Okta, for this very nice introduction. I also want to welcome you here on behalf of all the organizers. Andrew, we're here to celebrate Andrew, who is a very dear and important person for all of us. I'm sure there will be a lot of nice stories that we will hear about Andrew. Anyway, so I would also like to thank Sakina Benima, who has made this all possible. We're very grateful to her amazing support. Thank you. So without further ado, I would like to introduce our first speaker, James Maynard, who was a postdoc at CRM here when he proved one of the results that made him famous and led to his very recent Fields Medal. And he will speak to us about, I'm sorry, I didn't get your title. I just realized I don't have your title, I'm sorry. Half isolated zeros and zero density estimates. Thank you, James. I'm sorry about that.
Thanks a lot, Dimitris, for the introduction. And thanks a lot to my co-organizers for inviting me to speak here. It's always a pleasure to be back in Montreal, but obviously a particular pleasure to be here to celebrate Andrew's 60th birthday. So Andrew certainly had a large influence on my career in many different ways. But I think the thing that I admire most about Andrew in a mathematical sense is his sort of sense of mathematics. He has this sort of amazing intuition sense of mathematics, both in seeing talent in other mathematicians, knowing the right sort of environments to foster mathematics and real research and progress, and then also obviously in research itself. Sometimes this sense of mathematics can be slightly frustrating as a collaborator. There's certainly been many times when I've been talking math with Andrew, and Andrew has this amazingly sort of disarming and laid back manner, which sometimes gives me the sense that he kind of doesn't really know what I'm talking about. So we'll be talking to the blackboard, and I'll gradually be, even though I know Andrew, I had this even when I was a postdoc at CRM. I was at first slightly intimidated by Andrew, but he has this amazingly disarming thing. So within about 5 minutes, I was thinking, does this guy even know what he's talking about? And you have this sort of slight dismissive thing, and then suddenly Andrew will come up with some insight that completely floors you and really gets to the heart of the problem. And I don't understand how he keeps on doing this. He tricks me into thinking that he doesn't know what he's talking about, just to smack me down. Happy 60th birthday, Andrew. I hope you have many more theorems, and I hope you have many more opportunities to smack me down again in the future. Okay, so I only have half an hour, so maybe I'll get on to the math. So I'm going to talk about half isolated zeros and zero density estimates. And before I forget, everything I say here, joint work with Pratt, who's a postdoc with me in Oxford. And you might have seen some slightly earlier versions of this talk by either me or Kyle, or our preprint, but a sort of new development is there's an extra idea of Roger Heath-Brown, who showed that we could modify some of our arguments to get stronger results. So that's a sort of new development. So first of all, let me focus and remind everyone about zero density estimates. So we know that if you assume the Riemann hypothesis, then there's all these different fantastic consequences for the distribution of prime numbers. And that's maybe the main reason, or one of the main reasons, that we're even interested in the Riemann hypothesis. But if all you care about is those consequences for prime numbers, actually, often you don't need a result which is quite as strong as the Riemann hypothesis. That for results about, say, primes in short intervals, which is the commonly cited consequence of the Riemann hypothesis for primes, it actually wouldn't matter if there were just 1 or 2 zeros that were off the half line. The key thing that we need is that there's not too many zeros off the half line. So we need some control over the zeros of the Riemann zeta function, but we don't actually need them to all lie on the half line. And one very effective tool for measuring this is zero density estimates. So let n of sigma t be the number of zeros. So I'm thinking non-trivial zeros of the Riemann zeta function, such that the real part of the zero is at least sigma, and the imaginary part of the zero is at most t. So this is just counting zeros in a box. I could draw a little picture of the complex plane. So we have the half line where we believe, so this is the real part of S on the x-axis, the imaginary part of S on the y-axis. We believe all the zeros of the Riemann zeta function should be lying on this half line, and n of sigma t is counting the number of zeros in some box to the right of the half line, where the height of the box is t, and the box is going between sigma and 1. And so this is measuring how many possible counterexamples to the Riemann hypothesis there are at height t, where the real parts are at least sigma. And the key point is that we can unconditionally get some fairly good upper bounds on n of sigma t, and these unconditional estimates of n of sigma t can then serve as an unconditional substitute for the Riemann hypothesis from the point of view of proven results about prime numbers. So maybe the most important bounds of n of sigma t are that n of sigma t is bounded above by t to the 3 times 1 minus sigma over 2 minus sigma plus a little o1, and we also have a bound of t to the 3 times 1 minus sigma over 3 sigma minus 1 plus little o1. So this is by Ingham from 1940, I think. And this is by Huxley, building of work of Montgomery and Clash from 1972. A quick calculation shows that this bound is better when sigma is smaller than 3/4, and this bound is better when sigma is bigger than 3/4. In the subsequent years, essentially, Ingham's result has basically not been improved at all, so it's been good for 80 years. Huxley's result is 50 years old. It has been improved when sigma gets closer to 1. You can prove rather stronger things, but at least in the region when sigma is close to 3/4, this has not been improved for about 50 years. And it's this, for many applications in the primes, it's this crossover point when sigma equals 3/4, which is the key limiting factor. So there's a crossover at sigma equals 3/4, and this is the key limitation for many applications to primes. So in particular, if you proved some new zero density estimate that said there were very few zeros in some vertical strip around 3/4, overnight you would have improved on a whole load of different estimates for primes to do with primes in short intervals, primes in almost short intervals, and lots of related questions as well. But unfortunately, this estimate of there being at most t to the 3/5 zeros around sigma equals 3/4 up to height t is the key limitation for lots of different results about primes and has resisted all improvements for at least 50 years. However, the point is that these are unconditional substitutes for the Riemann hypothesis. And so if you have that n of sigma t satisfies a bound of the form t to some constant a times 1 minus sigma plus little o1 for fixed a. And I guess I'm thinking of this for all values of sigma between, well, 0 and 1, but maybe 1/2 and 1 is the key range. Then you get a asymptotic formula for primes in short intervals, provided the length of your short interval is bigger than x to the power 1 minus 1 over a. So in particular, if you put these two results together, this gives you a bound of this form with a as 12/5. And again, you can improve that 12/5 if you could improve results just in the neighborhood of 3/4. And that gives us essentially the best results for primes in short intervals, where we can get an asymptotic formula for primes in short intervals of length x to the 7/12. So that follows automatically from these zero density estimates, and that's still essentially the best known results. So, okay, this is kind of still roughly the state of the art for getting asymptotic formulas for primes in short intervals. But I'd like to start off with one observation. So firstly, n of sigma t maybe doesn't take into account the location. So this is both a good thing and a bad thing. The fact that it's just counting the number of zeros means that it doesn't care about where in the box these zeros lie, means that it can apply automatically to lots of different problems. And so that's why these zero density estimates are very flexible and useful. But on the other hand, you might wonder about what patterns of zeros there are. So based on these results, for the point of view of counting primes in short intervals, you only have to worry about zeros which are very close to the 3/4 line. And so you can imagine like zeros on the 3/4 line. And if they were scattered randomly, actually this wouldn't have any issues at all for counting primes in short intervals. So you might expect that actually for any generic distribution of zeros on the 3/4 line, this wouldn't, even if there were lots and lots of zeros, of course we expect there to be no zeros, but even if there were lots and lots of zeros on the 3/4 line, this wouldn't actually obstruct further progress on counting primes. So the question then would be, what would be possible bad configurations of zeros along the 3/4 line, which could obstruct progress to primes, and is there any way that we could rule out these configurations of zeros or make use of these configurations of zeros in some other way? And there is one fairly easy to see obstruction to zeros, the zeros of zeta of s lined up in various vertical arithmetic progressions, then this would obstruct progress. And you wouldn't, so I may be being a little bit vague about what I mean by vertical arithmetic progressions, but if the zeros on this 3/4 line come in lots of these clumps where they look like vertical arithmetic progressions of zeros, then at least at first sight, you wouldn't get any extra cancellation in sums over zeros that appear, and you wouldn't expect to be able to improve upon these bounds unless you somehow showed that there were fewer zeros. So this obstruction of zeros lying in vertical arithmetic progression certainly comes up in various other places. So things that look like vertical arithmetic progressions of zeros would cause problems for, say, Chebyshev's bias. So Rudnick and not Rudnick, Sarnak and Rubinstein assume the linear independence of the imaginary parts of the zeros as a sort of strong way of ruling out vertical arithmetic progressions of zeros, and vertical arithmetic progressions of zeros would really mess up things to do with Chebyshev's bias, because the zeros could correlate and conspire together. So this is certainly something that you need to rule out if you want to make progress in this sort of direction. But nonetheless, the ambitious dream might be step 1, show that the only obstruction to progress on whatever problem it is that you're interested in, either zero density estimates or estimates about primes or something, is somehow vertical arithmetic progressions of zeros. And again, I want to be a bit vague about what I mean by vertical arithmetic progressions of zeros, because a small perturbation is not going to change anything very much. So it's something that looks somewhat like a vertical arithmetic progression. And then the second step would be to use the structure of the arithmetic progressions to show that you can still handle things. So one way you might try and overcome these estimates is saying, even if I don't know how to improve zero density estimates, I could show that for the purpose of, say, primes in short intervals, the only obstruction to progress is if there are these bad vertical arithmetic progressions or something that looks like them. And then once I have this very strong kind of algebraic structure on the zeros, I suddenly know an awful lot more about the primes, and maybe I could hope to contradict that using some other evidence, or to try and show that actually we can improve zero density estimates for these arithmetic progressions, and therefore we're in a good situation regardless of what the situation is. So the only problem with this ambitious dream is that I don't know how to do step 1 and I don't know how to do step 2. It still remains a dream for now, even though I would like to do both step 1 and 2. It's not for lack of trying, but at least in joint work, we're able to do some sort of very weak form of this ambitious dream, which can be a sort of proof of principle in this sort of direction, that maybe this isn't a completely hopeless task, even if I'm still really stuck on both step 1 and step 2. I guess you might not need to do it quite as concretely as step 1 and step 2. You might be able to have something that combines them, but maybe I'll write this out as my first, as the main result that I like to talk about, which is if you assume that there's a certain like rigidity in the real parts of zeros, then we can carry out a strategy along these lines and get improvements to zero density estimates and correspondingly results about primes in primes in short intervals and things like this. So, so there's a theorem, and this is so Kyle and I have a paper on the archive where we carry a version of this result out, and then Roger Heath-Brown mentioned that we can tweak one of our lemmas and improve it and get rather stronger results. So Roger claims that he doesn't really deserve to be a co-author on this, but since he's not here right now, I'm going to put him down, and he can't object. So, as I said, I need some sort of assumption about the horizontal rigidity of the zeros. So, for an easy way to state this is assume the zeros of zeta of s lie on finitely many vertical lines. Then we can prove improve bound for zero density estimates, which is actually known as the density hypothesis, that n of sigma t is bounded by 2 minus 2 sigma. And this density hypothesis is, in many circumstances, essentially as good as the Riemann hypothesis for results about primes. So, for example, you get an asymptotic formula for primes in short intervals whenever y is slightly bigger than the square root of x. So under the Riemann hypothesis, you get a result of this type, and you can improve the x to the epsilon to a log factor. I guess we haven't tried to squeeze as much out as possible to make this epsilon precise, but essentially this is the same sort of range of results as the Riemann hypothesis. And similarly, you get primes in almost all short intervals of length x to the epsilon and things like that. So you get lots of nice consequences for primes if you assume this somewhat strange statement about the zeros of the Riemann zeta function line on finitely many vertical lines. But the key point about this assumption on finitely many vertical lines, from my point of view, is that this is still compatible with vertical arithmetic regressions of zeros. And so this is, in some ways, showing that this is not the biggest issue, and we can do some at least weak version of this ambitious dream. So hopefully everyone is at least somewhat happy with what the main statement that I'm talking about is. In the minutes remaining, I'd then like to give a vague flavor of how we prove a result like this. And this is where the so-called half-isolated zeros from the title comes in. If the zeros lie on finitely many vertical lines, so I'm not going to try and prove the density hypothesis in this result. I'm just going to talk about how we could make a small improvement to the previous bounds, and then hopefully that will give you, will at least convince you that you can do better than what we had before. And once we've overcome this limitation at 3/4, then there's a question as to how much you can quantitatively improve things. And it turns out, with thanks to Heath-Brown's modification of the argument, you can actually get all the way to the sort of most ambitious unconditional result of this type. So if the zeros lie on finitely many vertical lines, then we know that we have sort of good improvements to n of sigma t, apart from in the neighborhood of the 3/4 line. So we only need to care about zeros genuinely on the 3/4 line. So for purposes of this talk, we might as well like ignore all other zeros and just concentrate on zeros on the 3/4 line. Concentrate on zeros on the 3/4 line, since these are the only problematic ones for improving zero density estimates. And we can think about what a picture of them would look like. So we now have the 3/4 line, and the zeros will all line up. We know that in some moderately long interval, let's say an interval of length t to the 1/4 or so, there can't be too many zeros. And so therefore the zeros have to come in different clumps together, where I'm saying a zero is close to another zero if it differs by maybe if it's at height t, if it differs by log t cubed or something like that, some logarithmic power of t. So the zeros on the 3/4 line all appear in clumps where we're saying, say, row 1 is close to row 2 if they're both on the 3/4 line and they differ by at most log t cubed, and they're up at height t. And what we want to think about is not detecting all of these zeros, which we think is difficult and is very much like all the standard techniques for zero density estimates, but we want to introduce a new technique for detecting these zeros at the bottom of a clump. And these are the zeros that we call half isolated, because they might have several zeros nearby above them, but they don't have any zeros nearby below them. Call the bottom zero half isolated. And then maybe the key proposition is that we have a new zero detection mechanism that's rather different to the sort of traditional zero detection techniques, where we can detect these half isolated zeros using very short zero detecting Dirichlet polynomials. Proposition, there is a Dirichlet polynomial, so I'll call it d of s, which is going to be a sum over integers of length t, I'll say to the power 1 over log t. So the point is it's a very short Dirichlet polynomial. So it's a Dirichlet polynomial, so it looks like 1 over n to the s, and then it has some coefficient dn, where maybe dn is bounded above by 1, such that rho is a half isolated zero, then d of rho takes a large value. So it's bigger than 1 over log t to the power 100 or something like that. So the standard way of proving zero density estimates is to find Dirichlet polynomials that take large values at zeros, but the downside is that often the length of the Dirichlet polynomial has to be quite long. And it's this length of the Dirichlet polynomial that means you are limited in how well you can do in terms of mean value theorems and large values estimates for Dirichlet polynomials. Whereas the key point here is that we get these very short Dirichlet polynomial detecting half isolated zeros. And so in particular, we can estimate all moments of these Dirichlet polynomials. We can show that they have sort of square root type cancellation, and that automatically means that the number of half isolated zeros satisfies the bound, which is like the density hypothesis. So since every clump of zeros comes with a half isolated zero, this fact means that there's few half isolated zeros, and so there are then few zeros that appear in any short clump of zeros. So provided this clump is not too big, we get improved zero density estimates for any zero in that clump. But this doesn't necessarily improve anything if you had a really big clump of zeros. This improves things for small clumps. But that means you only need to concentrate on when you have lots of zeros really packed very tightly together on the 3/4 line. And when you have these zeros very tightly packed together on the 3/4 line, you can modify some of the previously existing zero density technology to make use of this additional structure that you have on the zeros. And so I'm basically out of time. Proposition 2, you can modify traditional zero detecting techniques to exploit large clumps. So in particular, the limit of our technology for zeros on the 3/4 line is actually zeros which are detected by a particular Dirichlet polynomial of length 2/5. And for these Dirichlet polynomials of length 2/5, we're to count the large values, we're limited by our kind of crude estimates for both the fourth moment and the sixth moment, if we could have a tight bound for the fifth moment, then we would get much better results. But if there's a large clump here, you can introduce an averaging over the clump, and this allows you more flexibility and essentially wins you a factor in these mean value estimates, which is to do with this, which is proportional to the length of the clump. And so in particular, if the clumps are large, this allows you to improve on traditional zero detecting techniques and allows you to improve on zero density estimates. And so therefore, by combining these two propositions, one for small clumps and one for large clumps, you can then get an improvement on zero density estimates, and therefore an improvement for the ranges when you get primes in short intervals and things, assuming the zeros all are on finitely many vertical lines. So I think I'm out of time here, so maybe I'll stop there. I've said everything I'd like to. Thanks a lot for listening, and happy birthday, Andrew.
Great talk. Just a minor quibble. Do you really just mean one Dirichlet polynomial for that proposition, or is there a family of Dirichlet polynomials, one of which detects each zero?
Okay, so I guess in principle, it's, so I think at least as we write in the paper, we have some family of logarithmic size, but I would have thought that if you have large values of Dirichlet polynomials of a logarithmic size, and you know that one of them is big, you could have some linear combination and only lose log factors or something. So I think you can probably write it in this form.
A couple of questions. So, so how much can you blur finitely many vertical lines? I presume you can be close to vertical lines.
Yeah. So the really important point is that somehow, if you're in one of these clumps, they stay away from any other clump. I mean, you could have at height t, you have vertical lines that are separated by something like log t cubed over log t. So you really only need a fairly small amount of separation, but the key point is that somehow these clumps have to be separated away from one another.
I was also thinking just, you don't really need a line, you need with.
Yeah, you don't need a line at all. Yeah, but it's important that, so my belief is that actually it's not vertical arithmetic progressions of zeros which are the problem per se. It's things that in the vertical direction look like arithmetic progressions of zeros, but in the horizontal direction look like they're smoothly moving from 1/2 to 3/4 and back again. And so you need something to stop the real parts drifting all the way to 1/2 by making lots of small steps. Yeah, provided you have sort of some bounds either side, and you're allowing them, you could allow them to vary between sort of 3/4 minus a little bit and 3/4 plus a little bit, and that'd be okay.
Okay, one point. I mean, you didn't mention large character sums, but you know, if a character sum size q to the quarter, you can very precisely locate the zeros.
Yeah,
and you know, step two. I mean, Igor, I guess, and Roger have papers on this, and Sound and I. Yeah, I mean, that's a long-standing ambition. But have you looked at that? Do you have any hope of doing anything with zeros where we really know where they lie pretty precisely?
Okay, so I have looked at that as well, and I failed at that as in the same way that I failed here. I guess, yeah, for this project, I have been a little bit more focused on this, but I certainly know, because I guess that. So the interesting thing is that in your case, so I mentioned that it's what we call bows, these bows of zeros that move from the half line to the 3/4 line and backwards that look like an arithmetic progression in the vertical aspect. For the large character sums, you do actually get these sort of bow-like shapes happening with this precise location of zeros, that they do look like an arithmetic progression approximately. All the action is happening much closer to the one line in that situation. But there's certainly some clear similarities there. But yeah, at the moment, I feel that all the techniques I know for detecting zeros seem to just fail. Well, I was going to say miserably, but in some ways they only fail by a little bit, but they just fail a little bit too much for detecting these like strange patterns, which are also the patterns that appear for large character sums.
We did nothing really. I mean, none of the papers do things that feel very familiar to your techniques. So maybe.
I have one actually. So you mentioned about arithmetic progressions, but I didn't catch where it actually comes into play. So you have to rule out some pattern.
Yeah, so I'm thinking, okay, so if say you want to prove an asymptotic formula for primes and short intervals, then pi of x plus y minus pi of x minus the, maybe y over log x, you can approximately think of as something that's coming from the terms from the zeros, which looks roughly like x to the row minus 1 for zeros row up to height x over y. And if you had cancellation in the sum, and if you're assuming some rigidity or something, you can think of all of these zeros as lying on the 3/4 line. So each of these terms has size x to the 3/4, and then it's essentially some exponential sum in the imaginary parts of these zeros. And you might hope that for a generic distribution of these zeros, you'd have decent cancellation in this exponential sum. So even if there's lots of terms, you'd be able to improve on zero density estimates. But if there's some bad value of x, such that x to the I gamma is always very close to 1, for example, for virtually all of these zeros on the 3/4 line, then you would have no cancellation in this sum, and this would be equal to roughly the size of the number of zeros in the 3/4 line. And one of the key aspects of how x to the I gamma can always point towards 1 would be if the zeros were lying in an arithmetic progression with common difference 2 pi over log x.
Right, but I mainly meant in the proofs of your propositions.
Yeah.
Do they come into play? Did you have to rule out things like that, or?
No, so we actually don't carry out this step 1, step 2 strategy, and we somewhat sidestep this. But there's certainly things that are very closely related to that, and so there's like interesting questions connected to the sort of inverse Littlewood type problem that would be much more of the flavor of this genuine arithmetic progression. So we show that there's these large values whenever there's this half isolated zero, which is somehow detecting some discontinuity in the local distribution of zeros. And my guess would be that there should be similarly a very short Dirichlet polynomial that takes a large value if there's a discontinuity that looks like the zeros, there's some violation of the zeros locally looking like some union of approximate arithmetic progressions. I don't know how to solve that inverse problem, and I think that's actually a super interesting problem, although I'm completely stuck on it. And it's connected to this inverse Littlewood question, which kind of has appeared in additive combinatorics before. And I also think it's a very interesting problem, and I also have no ideas of how to solve it. But yeah, my guess is that extending the technique for this large values of a short Dirichlet polynomial, half isolated zeros, this should extend unless the local distribution around the zero looks like a union of vertical arithmetic progressions. So we sidestep it by just detecting this discontinuity in a kind of crude way with this half isolated zero.
Yeah. So I guess we should thank James again and continue the discussion after the break.